One day, our universe will come to an end. The last stars will fade away, taking with them any remembrance of what was once a colorful and vibrant cosmos. No matter what we do or where we go, even if humanity endures forever, we will need to adapt to cross this barrier. And for that, we will need to learn to live around a black hole. But is it even possible? In this video, we will learn that it is, as long as certain conditions are met. In our first attempt, let's start with something straightforward. We'll choose a black hole with a planet in orbit. In this initial scenario, the black hole is stellar, meaning it's not a galactic monster like the black hole at the center of our galaxy. Instead, it's a black hole with a mass several times that of the Sun. The planet is much like Earth. Here's an interesting tidbit. If our Sun were magically transformed into a black hole with the same mass it has today, all the planets would continue to orbit in the same way. I can already envision some of you typing angry comments, but this is a fact. The main difference is that the Sun would be compressed until it's a bit larger than Mount Everest, and it would lose its brightness in the process. There's no risk of jets or winds here because the black hole isn't feeding on anything. Even Hawking radiation, which slowly causes black holes to evaporate, is too slow to directly affect the planet. So far, everything seems perfect, right? Wrong. Just a month later, we realize there's no longer any civilization on the planet. Humanity has gone extinct. Since this planet doesn't receive a source of energy, it becomes a frozen, uninhabitable world. It's impossible to produce food on the surface because temperatures are too low for life as we know it. The entire planet becomes a kind of frozen wasteland with almost no signs of life. And here lies our biggest mistake in choosing this planet. We were so focused on finding something Earth-like and the dangers of a black hole that we forgot the most crucial factor. There's no heat source other than the planet itself, and that's insufficient. But don't worry, pretend it never happened. We still have a few more attempts to explore. Second attempt. This time, let's choose a stellar black hole, one with mass just a few times larger than our Sun, and pair it with a planet similar to Earth in orbit. However, unlike the last attempt, let's suppose this black hole is feasting on a companion star, specifically, a binary X-ray star. Now, the accretion disk forming around the black hole becomes a heat source, along with the star being devoured. Something curious starts to emerge. The planet's orbit seems a bit peculiar. It doesn't follow the type of nearly circular and perfect orbits we're accustomed to with our Sun. But, hey, the planet has survived near a black hole for all this time, so it seems we can overlook this, right? Perhaps the orbit follows a pattern we didn't initially grasp. What's important is that this time around, the surface isn't frozen. We can even spot liquid water and greenish areas on the planet, reminiscent of how Earth looks from space in its early moments. Civilization seems to adapt well to these conditions, despite the higher temperature than Earth's. Okay, it seems like we've finally got it right, learned from our past mistake, and found a place for humanity to thrive around a black hole. But then, when we look back at the system, the planet is gone. After examining telescope images, we realize an energetic wind escaped from the black hole star system, striking the planet directly. This fried its atmosphere and altered its orbit, causing it to approach the black hole too closely and be devoured in the process. In a matter of days, the planet was transformed into a noodle, sucked into the black hole. And just when we thought it couldn't get any worse, the star explodes a few years later because the black hole consumed much of its matter, leading to its collapse. Even if it wasn't the energetic winds emitted by the black hole, the planet would likely have been devoured at some point. This is the famous three-body problem. The motion of orbits becomes chaotic. Now, even if the planet hadn't been swallowed, the star's explosion would have fried it or at least ejected it from the stellar system, destined to freeze in space. It seems we're getting into a pattern here, and perhaps the issue lies with stellar black holes. They can be more dangerous than supermassive ones, as it's nearly impossible for an orbit to remain stable around stellar black holes. The slightest disturbance would change the planet's course, rendering any civilization on its surface far too vulnerable. Third attempt. This time, we'll get it right. Instead of a small black hole with only a few times the mass of a star, let's consider a supermassive black hole, one with millions of times the mass of our Sun. To avoid the cold, let's assume this supermassive black hole is consuming matter at a high accretion rate. What would happen to a planet orbiting this massive entity? First, we need to consider that the planet will be far enough from the black hole. Before we even choose the planet, it's struck by radiation, which destroys its atmosphere. However, we have a special name for black holes that feed at high accretion rates: quasars. Quasars are so luminous that when they were first discovered, many astronomers mistook them for stars. Black holes that feed at high accretion rates can be considered quasars. The challenge in trying to find a habitable zone around a quasar is that they are extremely energetic, far more energetic than a planet could endure. Much of the spectrum emitted by such objects falls in the X-ray, ultraviolet, and even gamma-ray wavelengths. You can probably imagine that even if we managed to place civilization around one, it would be a harsh environment for humans. So, let's steer clear of hungry supermassive black holes. Fourth attempt. This time, we'll choose a supermassive black hole with a low accretion rate, much like the M87 star. The first black hole for which we captured an image. This black hole strongly resembles Gargantua from the movie Interstellar. If you've seen the film, you're aware that planets can orbit such a black hole. I know that movies are generally terrible sources of scientific facts, but in this specific movie, physicist K. Thorne, a Nobel laureate, assisted in selecting the type of black hole that could host planets with life and habitable zones. The habitable zone around an object is the region where liquid water can exist. Each object has its own habitable zone. If we were to place a planet around this black hole, it would resemble the scenario depicted in Interstellar. Just like in the movie, everything seems to work. The planet can't be too close to the black hole because energetic winds are continuously emitted, and they have enough energy to vaporize the entire planet. Instead, we'll position the planet a bit further away, and at first glance, everything seems to function well. We have a comfortable temperature and an energy source coming from the black hole's accretion disk, which even lights up the sky. The only drawback appears to be the climate, as if there were no distinct temperature gradient. The entire planet remains at the same temperature because the planet only receives a specific wavelength, enough to keep it warm. Furthermore, there's no precise definition of a year or day due to gravitational effects. Light is everywhere on the globe all the time. Now, it may seem like this could be a place where life could thrive despite these challenges. However, over time, any civilization living on such a planet would realize that it's very difficult to produce food. People would fall ill frequently, and the birth rate would decrease significantly. In no time, the civilization would face extinction because many wouldn't survive this system. It's remarkable and somewhat unexpected, as this seemed to be exactly the kind of place we were seeking, within the habitable zone with no risk of an energetic event striking the planet with too much energy. Then we puzzled over what happened, and finally, we understood. Some complex and essential molecules for life require photons of different energies to break down. Think about it this way: we know that the sun emits a peak of visible light, which is enough to give us energy on Earth. But the sun also emits in lower intensities both more energetic and less energetic waves. Even if some of these photons are too energetic for us, such as UV radiation, they are still essential for breaking and transforming molecules that are crucial for life. However, when we place a planet where only one type of wavelength arrives and only one temperature exists, it would eventually affect the inhabitants. It's an indirect and unexpected consequence that would still lead the civilization around the black hole to collapse. So, once again, we'll reset our experiment because it hasn't succeeded yet. Fifth attempt. This time, we're going to choose a supermassive black hole with a not very active accretion disk, much like the previous example. But this time, we'll place bright and massive stars around it. The idea is brilliant. The only reason the last civilization didn't succeed was due to a lack of more energetic photons. Otherwise, all conditions were favorable. Another piece of good news is that it's much more common to find supermassive black holes surrounded by stars. In other words, the type of black hole we just created in this example is quite common in the universe and easy to find. Additionally, the planet's view should be stunning. The sky will be extremely starry, much more than here on Earth, with stars of various colors. Perhaps too many stars. This makes us realize that the planet's sky is incredibly bright, making it impossible even to look up. Imagine being under the sky on Earth, but the sun is thousands of times brighter. Now multiply this brightness by several stars until the entire sky is filled with them. It would be impossible even to be outside, as particles called neutrinos are passing through your body right now. They are known as silent killers precisely because they interact very weakly with everything around them. Near our sun, our closest source of neutrinos, they're never a problem for us. But if we had thousands of intensely shining suns nearby, it would be problematic. They're energetic enough to affect the planet's chemistry and atmosphere, including humans. It's disheartening to know that we've come so close to success, and something invisible destroys our hopes. But there is one last chance, one final attempt. So, let's revisit this video one more time. This is our final attempt. This time, we're going to be meticulous in choosing a supermassive and solitary black hole. It's not consuming anything, and there are no nearby stars. The Hawking radiation is so faint that it's nearly imperceptible, not interfering with the planet. At first glance, this scenario doesn't seem to offer a habitable zone because the black hole doesn't provide an energy source. You might think this resembles our first attempt's mistake when the planet lacked an energy source, leading to freezing. But please, be patient, as I'll explain why this choice is our best option. Think about the movie Interstellar and how they dealt with a time dilation problem. Essentially, when two astronauts go to a planet near a black hole, time passes much more slowly for them. When they return to the spacecraft, they realize that years have passed while only hours elapsed for them. This is a real effect, albeit measured on Earth to a much lesser extent. But what many people don't know is that this effect applies to the wavelength of light as well. Imagine that the astronaut staying on the spaceship is sending a signal every second. The astronauts on the planet will receive 60,000 signals per second because 2 hours on the planet equate to years on the spaceship. Now, transform this to light frequency. If the astronaut on the ship sends a low-frequency light signal, the astronauts on the planet will receive this signal with a much higher frequency. Higher frequencies mean more energetic photons, which could heat the planet similarly to how the Sun does on Earth. The universe itself offers a frequency, a remnant of the Big Bang, called cosmic microwave background, CMB, radiation. For us on Earth, the CMB radiation is almost imperceptible with its mere 2 Kelvin temperature or -455.07 F degree. We can only measure it with special telescopes. But for a planet close enough to a black hole, the CMB radiation could be dilated to wavelengths similar to that of the Sun. In other words, the CMB radiation would serve as an energy source for the planet, even making liquid water possible. Okay, so we've solved the energy problem. Issues associated with potential destruction by the black hole or stars have been resolved because we're now in a safe zone. The civilization could live around this black hole. The only problem is that day and night would not be concepts for this planet because the CMB radiation comes from all directions of the universe. The entire planet would be encompassed by this artificial star, creating an eternal summer. Day would be endless, and this planet would have the same climate year-round. It would be like living in perpetual summer, with no concept of changing seasons or day and night. Future generations wouldn't know what a dark sky is, perhaps only by the point in the sky where the black hole is. That's where this civilization might have some idea of what a dark sky is, or at least a piece of it. Even this wouldn't be forever. Eventually, something could reach the black hole, even if it took hundreds of thousands of years. Furthermore, the CMB radiation would weaken year by year as the universe cools. It would take quite some time, but it too would have an expiration date. In other words, it would be a temporary shelter for humanity. If the question is whether we could live around a black hole, then under extremely specific conditions, the answer is yes. However, these conditions are so specialized that finding a system like this in the universe would be incredibly challenging. Nevertheless, the universe is vast, and there's a non-zero probability of such a system existing somewhere out there. The lesson from this video, in my view, is that no matter how advanced our technology or understanding of the cosmos becomes, we will never be able to achieve immortality. Let's simply accept this fact. Thank you, and until next time.